In this lesson, we'll be looking at models of light. So we'll be analysing the experimental evidence that supported the models of light proposed by two key figures, Sir Isaac Newton and the Dutchman Christian Huygens. So these two scientists had conflicting models of light, conflicting views. Newton was a proponent for the particle model of light, and Huygens was a proponent for the wave model of light. And by the year 1700, these two gentlemen had their ideas put forward already. And I should also emphasise that Newton's model was also called the corpuscular model. Corpuscular as in particle. So let's begin with Newton's model of 1672. Now, for the HSC, you don't need to memorise these dates. They're just there to give you some idea of what's happening at what particular point in time. So Newton proposed quite simply that light is a stream of particles, called corpuscles. And he believed that they were elastic. So these were elastic particles. They could bounce around and do things, and they had different mass. And different mass, he believed, is what gave rise to different coloured light. So he believed that red light had different mass to blue light, for example. And he also believed that they travel at finite speed. So there's a particular speed that these corpuscles travel at. It wasn't really too far from the truth. We now know that light does travel at a particular speed. And using this idea of corpuscles, he could then explain the properties of dispersion, reflection, and refraction. And he argued that light doesn't show diffraction. So light doesn't, exhibit diffraction. So diffraction, a bit more about that later on, but for now it's basically when you place an object in front of a light source. Let's suppose I have a light source and the light rays are travelling to the right. Suppose I put like a hunk of wood. You should still see the light. That's what diffraction is. The light bends around the object. Much like sound, right? If you are sitting in a room and there's a speaker outside the room where the door is, you should still be able to hear the sound from outside the room. That's the diffraction of sound waves. And he explained that light travels in straight lines. Light travels in straight lines. Which it does. You now know that it does. Due to their inertia. So they've got the property of inertia. These particles, every particle, every object with mass has inertia, a tendency to resist motion. And so with that, he was able to explain reflection of light. It's a very simple idea in Newton's picture, because the particles are basically repelled. So suppose you have a flat surface like a mirror, a plane mirror. Plane means flat. You've got incoming corpuscles, from a light source. He believed that reflection occurred due to the corpuscles being repelled by the reflecting surface. They simply bounce back. We know this is true. However, the idea that they're repelled doesn't really fit the picture that we have nowadays. But he was sort of right in the sense that reflection occurs when light bounces off the surface, right? He also explained refraction. Refraction just means the bending of light. Bit of a weird idea. He proposed that refraction occurs due to the corpuscles the corpuscles were attracted to the refracting materials themselves, which is a bit weird, making them travel faster in the material. Put a question mark after that, because we now know that that's not the case. Light travels slower in materials, it basically gets slowed down, and they're not really attracted. So that's refraction. He also explained dispersion. We're all familiar with dispersion. Dispersion is when you have a piece of glass, let's say you have a glass ornament on your table in your living room, and you have light coming in from the sun through the window, through a door, and it hits the ornament. You'll see like a rainbow coming out of it on the table, right? That's dispersion. Dispersion is a splitting of light into its different constituent colours. And he explained dispersion due to the different masses of corpuscles, as I mentioned before. He believed that the light particles, the corpuscles, have different masses. Different masses give different colours. And this wasn't actually experimentally verifiable by Newton. Okay, he failed to sort of show experimentally that this was the case. So this was theoretical. What his model couldn't explain was polarization. This will be, and I'll talk about this later on in upcoming videos. Polarization, this is basically when light has a changing electric field along only one plane. So the electric field is only going about one plane. And there was no direct experimental evidence at the time for this as well, to prove that light did this. And also there was no evidence to demonstrate that light was a particle, despite its theoretical successes according to Newton. So that's Newton's picture of light. It's a particle. It's got a certain mass, and it can do all sorts of things like reflect, refract, and disperse. On to Huygens, the Dutchman Huygens. So Huygens' model, okay, proposed in 1678, a bit later than Newton. So Huygens proposed that light is a wave. And it travels as a longitudinal pressure wave. In other words, he believed that it was sort of like sound. Sound is a longitudinal wave. Okay, longitudinal waves oscillate back and forth across one plane, as opposed to transverse waves, in which the particles oscillate perpendicular to the direction of motion of the wave. And he believed that this longitudinal pressure wave travelled in some elastic medium, some ether. Okay, something that fills all of space. He explained how light travels in straight lines, just like Newton explained light travels in straight lines. Okay, and this is using what's known as Huygens' principle of secondary wavefronts. It's a very simple, I should say wavelets. It's a very simple principle to explain. So basically, light propagates by each point on the wavefront, acting as a source of secondary wavelets. I'll explain it now. So suppose you have an initial wavefront. Okay, initial light wave traveling through space, going to the right. As it did so, it would, so each point on the wavefront would act as a individual point source of secondary wavelets. So it would look like this. Okay, that's what Huygens believed. And you would have this new wavefront here. And as the wavefront propagates through space, you have this new wavefront forming at some tangent to the secondary wavelets. Okay, these are the secondary wavelets, these semicircles. More on this later when I talk about properties of light. But for now, he just proposed that light travels in straight lines from one point to another in space due to these secondary wavelets, these semicircles forming from initial wavefronts. And hence he was able to explain how light coming from a point source produces spherical wavefronts. Okay, so I'm constricted here to two dimensions, the x and y plane on my device. But just imagine that these are three-dimensional spherical wavefronts. Huygens also explained the idea of reflection, okay, using what's known as Huygens' principle. Okay, the same idea that I've just explained before. Okay, so when light bounces off a surface, a plane mirror, let's say, the wavefront progresses through space, and you've got the initial wavefront forming secondary wavelets, which then forms a new wavefront. I'm not going to get into that because that's what I just explained now. He also explained refraction using his same principle of secondary wavelets. And he assumed that light travelled slower, correctly, in denser materials. So he was right about this, Huygens. Light does get slowed down. He also explained the idea of diffraction. As I mentioned before, it's the bending of light. It's the spreading out of a light wave when it enters a gap or an edge or some small object. Okay, and he qualitatively described this using his principle. So diffraction was explained well, and that's Huygens' model. So Huygens' model used the idea of wavelets. Okay, that light was a wave, propagates through space, and there are things called secondary wavelets which exist, which can help explain reflection, refraction, and diffraction. So let's now come up with some conclusions. So for each of these models. So here are the conclusions. So the first conclusion we can derive is that neither model explained all the observable phenomena, wave phenomena, satisfactorily. Neither model could explain. Let's put everything here for now. So neither model was successful in explaining all phenomena of light. And turns out that looking at observational evidence, experimental evidence in subsequent years, so around the early 19th century, these two guys, this Englishman named Thomas Young and this Frenchman named, I can't pronounce his name, let's keep it as A-J Fresnel, they independently demonstrated interference phenomena. That interference phenomena could only be explained if we treated light as a wave. So showed experimentally proved wave model through interference. So they did this independently. One guy was in England, one guy was in France. Interference is when you have two waves coming in, meeting up, and either combining to give a bigger wave or cancelling to give no wave at all. Okay, more on this later on. It's basically when two light waves interfere, right? They come into contact with each other. There was also observations of polarization at the time that led Young and Fresnel to return back to the idea of light being a transverse wave rather than longitudinal wave. So Young and Fresnel proposed light as transverse, and they were right in this as well. We now know that light, all forms of electromagnetic radiation, are transverse waves. And then another guy came along in the 1850s, a Frenchman named Foucault, I don't know if that's how you pronounce it, and he measured the speed of light. Measured the speed of light in water. And he confirmed Huygens' prediction that light would travel slower in water than in air. So equals confirmation of Huygens. Okay, so another thumbs up for Huygens' model. And also you had Maxwell. So I should put here 3 Foucault, 4 Maxwell. Maxwell, in the 1860s, as I mentioned previously, theoretically showed the existence of electromagnetic waves and their production, and then Hertz, in the 1880s, experimentally proved the existence of electromagnetic waves, and that supported the wave nature for light. So Newton's model wasn't really that supported by experiment at the time, and hence Huygens' model pretty much won at the time, thus far. And we'll see that in the 20th century, this idea of light being a wave sort of wasn't really that accurate. We'll see that light is also a particle, but this is showing you. So this silver stop point shows that you need experimental verification for theoretical ideas. Okay, theory and experiment are two mutually inclusive entities. You can't have one without the other. That's how science works. That's how progress works. So that's Newton's and Huygens' models of light in a nutshell.